Hi, my name is Kevin Winter. I'm currently at the University of Massachusetts in Amherst working with Dr. Dan Sheldon. And I'm going to be presenting some work from two related papers, both dealing with this topic of exact inference for integer latent variable models. So integer latent variable models show up a lot as very natural models in population modeling. I'm mostly familiar with the problem in the domain of ecology, but it also shows up pretty much in exactly the same form in epidemiology and sociology, where we're talking about human populations as opposed to animal populations. But basically, we're looking at populations that change over time, where I'm interested in knowing how the population is growing or shrinking, maybe for an endangered species that I want to conserve. And so here's one example of a model that I've been focusing on, although we're not too dependent on which particular model we happen to use. So this is called a latent branching process. So this looks sort of like a hidden Markov model, where I have some series of observations of a population at a fixed set of times. And then there's some true variable, which is the size of the population at each one of those sampling occasions, which we call the abundance. And then that abundance has some population dynamics that govern how it changes from one time step to the next. In this case, it has two. One is that there's some number of offspring produced by each one of the individuals in the population. And then there's also a separate process, an independent process, where new individuals can enter the population in immigration. My goal, let's just say I want to do something pretty simple. I just want to do maximum likelihood inference to learn the parameters of maybe the offspring, the immigration, and the observation processes. So I need a function to compute the likelihood. This sounds like a pretty easy problem. But the challenge here is that what kind of unites all of these population models is that they have an unbounded support for the latent variables. So the latent variables are discrete, but they're unbounded. So most of my inference tasks end up including an infinite sum. All of my representations of these probability distributions are infinite vectors, and none of the traditional algorithms that I'd like to use for something like a hidden Markov model, like the forward algorithm, they just simply don't work. There's no way to implement them for these types of latent variables. There's a couple of existing solutions for these problems. I could use some kind of sampling strategy like MCMC, or I could just transform it into a finite problem by putting some bound on the domain, some conservative estimate about how many individuals could possibly be in the population. But in both cases, both of these solutions are approximate. They're not giving me the true likelihood, although they can usually get pretty close, and they're usually quite slow. And so what I'd like to be able to do is I'd like to be able to do exact inference. And what I've been going to be proposing is a method based on probability generating functions. So this is a little technical. The basic technique of PGF inference is something that I've been developing in these two papers, and I'll be presenting at the poster. It's based on two main ideas. The first idea is a representational shift. I take all of the probability distributions in my method, and I replace them with the equivalent probability generating function representation. So the probability generating function is basically a power series that encodes all of the terms of my probability distribution. And then I'm going to, well, that's completely garbled. Thank you. It's OK. It printed great on the poster. So, but basically, what's nice is that all of the operations that I would define on my random variables have analogs in the sort of probability generating function space. So it's pretty easy to update my algorithms to use probability generating functions instead of probability distributions directly. And then, yeah, of course, that's also garbage. Most of the inference tasks, like performing marginalization, take the form of function evaluation, which you can't tell from this. They take the form of function evaluation. So I take a probability generating function, and I evaluate it at some number of points, and I perform my inference that way. Unfortunately, that's not implementable directly. So the second step, in order to actually implement this, is to use autodiff. So if most of my inference tasks are basically function evaluation, I need to be able to evaluate a probability generating function and some of its derivatives. I can explain why at the poster. I can basically use autodiff. So if you're familiar with autodiff, this looks fairly similar. We had to extend autodiff a little bit in order to get this to work. So there's some kind of cool autodiff techniques if that's something you're interested in. The end result is that we can do exact inference for a large number of different problems. And it's actually generally faster than doing any of the approximate methods that exist. So it's kind of a win-win. I'm very excited about it. Biased, but I think it's pretty impactful, I hope. If you're interested, I would love to explain more of it at my poster. Thank you.